90% students get isomerism wrong in coordination compounds. Just watch this video so that no more mistakes in isomerism identification. Hello students, welcome to part 3 of coordination compounds. If not watched, watch part 1, part 2, then come to part 3. Let us see isomerism in today's video. So isomerism mainly two types, structural isomerism as well as stereoisomerism. Structural isomerism, how we can define structural isomerism? Differ in structural formula, or you can say different connectivity of atoms. Stereoisomerism differ in spatial arrangement of atoms. Stereoisomerism, the isomers differ in spatial arrangement of atoms. Let us start with structural isomerism first. Under structural isomerism, ionization isomerism, name itself indicating ionization isomerism or isomers differ in the type of ions produced. For example, see the coordination compound here 1, coordination compound 2. Both the coordination compounds having same molecular formula, the main criteria, molecular formula should be same, we know. Then, first compound producing coordination ion plus 2 2Br minus. Another compound producing plus 2 charge, same coordination sphere plus 2Cl minus. So, both are having same molecular formula, but they produce different types of ions. Such type of isomers known as ionization isomers. Phenomenon referred as ionization isomerism. Then you see hydrate isomerism. Hydrate isomerism differ in the number of H2O in outer sphere. Number of H2O, name itself indicating number of H2O in outer sphere. For example, you see compound here. CrH2O6 Cl3, CrH2O5 Cl, Cl2 H2O. Okay. In both the compounds, where you can see difference, in compound 1 there is no water molecule in outer sphere, but compound 2 there is water molecule in outer sphere. Molecular formula same. So those compounds which are having same molecular formula but differ in the number of water molecules in outer sphere are known as hydrate isomerism or hydrate isomers. Here 1 and 2 are hydrate isomers. Remember one statement. Here I wrote one more isomer with the above formula where 3H2O present here. It is not under hydrate isomers as there is anion and cation, as there is no anion cation separately. You mention here as there is no anion and cation separately. Why? Overall charge how much here? Overall charge it is 0, right? See in above examples there is cation here. There is cation, anion, cation, anion. But here there is no cation anion, it is completely neutral compound. Such type of combination is not possible. So under hydrate isomers we will not consider these because there is no separate cation and anion. Overall compound is neutral here. No separate anion cation. Hence we should not count such isomers. Okay. Next. Close the note. Third type, linkage isomerism. Linkage isomerism when ambidentate ligand shows difference in linkage. We know ambidentate ligand meaning ligand which can form bond through different donor atoms. Through different donor atoms like cyanide, isocyanide. Example see here. Here there is cyanide, donor atom is carbon. Here isocyanide, donor atom is nitrogen. Donor atom is nitrogen here. Here there is cyanide. Same ligand, that is ambidentate ligand, once forming bond through carbon, in other compound it is forming bond through nitrogen. Such type of compound where ligand link through different atoms referred as linkage isomers or linkage isomerism. 1 and 2 are linkage isomers. Okay. At any point of time, if you need time, if you want to note it down, pause the video, properly listen once again, pause the video, make notes along with me. Another example, PtH2O4 NCSNO2. So here now there is ambidentate ligand NCS, one more ambidentate ligand NO2. NCS can form bond through N. Similarly, it can form bond through S also. NCS, it can form bond through S also. That's why ambidentate. NO2 can form bond through N. Similarly, it can form bond through O. So how many combinations will get with these two? NCS, NCS, here SCN, SCN. NO2, ONO, NO2, ONO. Just we are changing these connections. Here nitrogen forming bond, here nitrogen forming bond, sulfur forming bond, sulfur forming bond. Remaining NO2, ONO, NO2, ONO, here also different bonds. So based on number of linkages, overall we get here 4 linkage isomers. Okay. Next, ligand isomerism. See, we did not change anything except these two, just we modified these two with different atoms. Different combinations, we got 4 linkage isomers. Ligand isomerism, ligand itself shows isomerism here, meaning here there is a ligand which is 1,2-dichlorobenzene. Same ligand, now isomer of ligand I am showing here, it is 1,3-dichlorobenzene, 1,2-dichlorobenzene, 1,3-dichlorobenzene. So there is difference in arrangement of ligand itself. So if there is difference in arrangement of ligand, then we can consider those isomers as ligand isomers, because see 1,2-dichlorobenzene, 1,3-dichlorobenzene. So ligand itself involved in the isomerism. Due to difference in identification or due to difference in position of atoms in ligand, isomerism arises. That's why it is ligand isomerism. Coordination isomerism. Here you see both cation and anion are coordination spheres. Both cation and anion are coordination spheres. Or you can, what you can write, both coordination spheres are complex ions. Both are same. And there is interchange of ligand between two spheres. See, both cation and anion coordination space here, but there is interchange of ligands. See here now. Here there is one coordination sphere and second coordination sphere. Entire comes under one compound only it is. First you see charge here. Chlorine is -1. Platinum NH3 is 0. So -1, total how many chlorine atoms? 4. So overall charge is -4. Overall charge is -4. Platinum exists commonly in +2 state if coordination number is 4. Previous videos we studied what are the common oxidation states. Whenever platinum is in coordination number 4, it shows +2. Here coordination number 4, copper also +2. So overall +2 we gave because we need +4 overall to balance it. Okay. Without changing coordination number, here it is 4, here also coordination number 4. Now what I am doing, out of 4 NH3, 1 H3 I am transferring to here. See, here I showed only 3 NH3, 1 NH3 placed here. And out of 4 chlorines, 1 chlorine transferred here. See, that's why we got second structure. Transfer, interchange of ligands. But in this case, what I did, out of 4 NH3, this time 2 NH3 here, 2 NH3 here. Out of 4 chlorine, 2 chlorine and here 2 chlorine. Okay. But this particular structure is not possible because overall charge you see, here copper +2, it is 0, Cl2 -2. +2 -2 overall charge is 0. Platinum +2, chlorine -2, overall charge is 0. Both the coordination spheres having 0 charge. Such combinations not possible. There should be cation anion separately. That's why we will not count this as under coordination isomers. See other combinations I wrote, NH3 1 here, 3 here. Previously 4 chlorine, so this time 3 we wrote here, 1 here. Similarly, CuCl4 -2 means charge it is. Charge I wrote overall. PtNH3 4. Charge, to check charge I wrote. See, these are not having any charges. Whatever I wrote here charge, to check charge. These are not ions, remember. Whatever the previous compound, it is neutral, right? Same like neutral compounds I wrote, but later I indicate the charge. Don't get confused. Here also same. After completion of arrangement, just I showed the charge overall. Here also I showed the charge after writing the compound. So compound not having any charge overall, remember. Cation anion are represented by using charge. Okay. So don't get confused. This -2 +2 -1 +1. These charges later assigned after writing these compounds. Okay. Total 4 coordination isomers possible because this one we are not counting. Next. Polymerization isomerism. See, polymerization isomerism, isomers with same empirical formula, isomers with same empirical formula are referred as polymerization isomers. However, it is not true isomerism. Remember, it is not true isomerism because their molecular formula different. is not true isomerism. Just one reference purpose we are writing here. So here same empirical formula if they show, those two are referred as polymerization isomers. See, one big complex compound given. It is entire one compound only, remember. Another compound here. I'm calculating empirical formula here. How many cobalt? 3, ammonia 9, NO2 9. If you simplify 9, 3, 9, 9, so you will get here 1:3:3. In another compound also see, cobalt, NH3 and then NO2. Ratio I used. Cobalt here 4, NH3 12, NO2 12. Ratio again 1:3:3. So both are having empirical formula same, hence these two are polymerization isomers. Which one? 1 and 2 are polymerization isomers. So that is about 6 types of structural isomerism. But out of these 6 types, 6th type is not true isomerism. But keep in mind, it is based on empirical formula we identify. Okay. Next, moving to stereoisomerism. Stereoisomerism, first type geometrical isomerism, here you can see. Second type optical isomerism. So geometrical isomerism, isomers differ in relative position of ligands around the central atom. Isomers differ in relative position of ligands around the central atom are GI, geometrical isomers. Okay, they differ in the relative position of ligands around central atom. For tetrahedral complex, which is sp3, coordination number is 4. Coordination number 4. So here no GI for these tetrahedral complexes. Reason, all positions are identical in tetrahedral. Tetrahedral, how it looks? For example, if I take here ligand, all 4 positions are identical. See, if there is a difference in relative position of ligand, then GI arises. Here all positions are identical, so you will not get any isomerism condition here. So all positions are identical, hence no geometrical isomerism in tetrahedral complex. Very important. No geometrical isomerism in tetrahedral complexes. Next, case 2. For square planar complex, pay attention, listen here, very important concept. Ma4, I wrote like this, square planar complex. You try to make diagonal pairs every time. Diagonal pairs meaning here A. I made one pair. Another A. Diagonal pairs, one more pair. So it is one particular arrangement. Is there any other possibility other than this? Just we are making those 4 ligands into random diagonal pairs. A, because all are same type, right? You will not get other possibility. No other possibility. So diagonal pairs we are writing. If no other possibility, straight away you can write no GI. We are converting those 4 ligands into 2 pairs. If you are unable to make another arrangement like this, which should be different from 1, here no other possibility, because 4 same type of ligand, how we can make different arrangement? So as there is no other possibility, here no GI. Simple method. Ma3B, directly here I wrote no GI. Why? No need to write every time structure like this, MAB, different combination. Just to focus on diagonal pairs. Or focus on A3B, you write into different combination. AB one pair, AA one pair. Any other possibility? If I interchange here AA, AB, again you will get same. So no other possibility, so here no GI. You can make random pairs, you no need to follow particular sequence. If you can make 2 such different arrangements, then we can say GI is possible. Next, Ma2B2 type. Here you can make arrangement C. Once I wrote AB and AB. One arrangement done. Other combination AA, BB. So A and B, 2 structures possible. A and B, 2 structures possible. That's why here GI possible. GI, how many geometrical isomers? 2 I wrote. 2 geometrical isomers possible because 2 structures possible which are different from each other. I showed here sequence C, cis. See square planar structure, I showed cis and trans. Above Ma2B21, I showed here like this. Cis and trans, square planar structure. Why it is cis? You see here. Why it is cis? either A or B, you take any one, either A or B. Here for example, if I consider A, both the atoms or both the ligands are of same type here, are on same side. Identical ligands on the same side, so cis. Identical ligands on opposite side, trans. Okay, that's what see. Diagonal pairs how we made. AB, I wrote here AB, 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 which is cis. That's what I wrote cis. Another diagonal pair you see. AA, no need to follow any sequence. You can write first BB also, no problem. AA, yes AA, BB, here there is BB. So one is cis, one is trans. So GI possible, how many? Two possible structures. Next, MA to BC. MA to BC, if I take MA to BC, combinations you can write, 4 ligands with us, write combinations. First AA combination, BC, AB, AC. GI possible 2. Similarly, MABCD, 3 combinations possible, 3 GI you will get. You try combinations once again by pausing the video. You can try once again. Pause the video, try once again. Now, whenever we are writing capital A, which is indicating bidentate ligand first of all. What is coordination number here? 4, right? But ligand only 2 given. Ligands mentioned only twice. Coordination number 4, how you will get? If it is bidentate, then only you will get. Bidentate meaning which can form 2 bonds. Capital letters AA, if you specify, it is bidentate. It is symmetrical. Why it is symmetrical? Because donor atoms are same. Here AA, both the donor atoms are same. For example, you take ethylene diamine which AA type. Ethylene diamine structure you already studied. Ethylene diamine having both the donor atoms nitrogen, NH2, NH2. Such type of ligand, general formula. If I write like this, only one possible arrangement here. Even if you shift AA, you will get same structure here, no GI for this. No arrangement possible. MAB twice. Bidentate, unsymmetrical this time. Unsymmetrical meaning donor atoms are different. Like glycine, glycinato, GLY. What is glycine? What is ethylene diamine? If you have any doubt, watch part 1, coordination compounds. Glycine of AB type. See, in part 1, I gave number of examples of ligands. Most familiar JEE mains question based ligands also I gave in part 1. If not watched, start with part 1 so that all doubts will be clear. GLY of AB type, GLY glycinato, unsymmetrical, where ligands, donor atoms of ligands are different type. Here you can make, for example, see, here M, I showed here A, see bidentate, so we are showing like chain here like this. It is one bidentate ligand, another bidentate ligand AB. First I arranged AB here, another BA arranged. Every time ligand should be placed only at 90 degree. You are not allowed to place ligand stretching like this and place at 180 degree. You are not allowed to, because bond stretching, it breaks, bond breaks. Only 90 degree you have to place. This time what I am doing, by keeping same like this, I am flipping AB. This one BA I wrote, here AB. So one more possibility. It is trans because identical atoms on opposite side. Cis because identical atoms on same side. Cis and trans shows GI, 2 structures possible. MAA AB type. MAA AB type. So one is, both are bidentate ligand by capital letters whenever we write bidentate. AA here symmetrical ligand, here unsymmetrical ligand. So here also no GI possible because no other arrangement. Here both are unsymmetrical ligands. So first I wrote AB, this one. Another one CD. This time what I did, second possibility, AB as it is I kept, but DC here CD flipped. So different arrangements, right? Here no possibility. So now GI is equal to 2 here. GI is equal to 2. So remember, bidentate ligands cannot be placed at 180 degree because of bond breaks. Why? As we are stretching the bond breaks, which is not favorable. Next, for octahedral complexes, see, octahedral complex is most important. Similar pattern we are using here now for octahedral complexes. See, coordination number is 6. Ma6, here no GI. Ma6, no GI, because if you write arrangements, you will get to know. It's not possible to make into different structures. You will get same, right? All are of same type. You will not get arrangements like this. Ma5B also no GI. Ma4B2 like this compound, like Ma4B2. Here it is possible. Two arrangements you can show. One is trans because Cl opposite side. One is cis, Cl same side. You can think about NH3. But whichever is differentiating, you see only 2 chlorine atoms, right? You focus on 2 chlorine atoms and check according to that, not according to ammonia. Only 2 chlorine atoms, so you can decide by using chlorine. Same side cis, opposite side trans. So GI it shows GI is equal to 2. Ma4BC, again you see combinations. See, previously we made 2 pairs, but it is coordination number 6 now. That's why every time we make 3 pairs. So structure number 1, structure number 2. Or you write like this, A and B, so that no confusion. Here A, B. See now. So here different arrangements we got. So GI is equal to 2. See, different arrangements meaning here we are making into different set of pairs. Different set of pairs. So here you will get A, BC, A, BA, AC, AA, BC. So two different sets we got. Each set having 3 pairs. Those 3 pairs should be different from others. At the same time, no need to follow any proper sequence. Those 6 ligands randomly you can arrange. But it should not be exactly identical. Keep in mind. Ma3B3 also same. Here you will get 2 GI arrangements. But here most important question, Ma3B3 type octahedral complex, special names given. 2 GI possible. How they named? Generally we know cis and trans. But here naming you see. Ma3B3 we arrange like this. If 2 atoms, same atoms, if 2 atoms in one plane and other is perpendicular to it. Here see 3 atoms of same type, 2 atoms in one plane, because it is one plane, right? It is. One atom is 2 atoms above and below, right? So 3 same identical ligands I am taking. Out of 3, 2 atoms in same plane, one is perpendicular to the plane. Such 3 arrangement, 3 ligands, if they satisfy this condition, then such type of isomers known as facial isomer or FAC isomer. Facial isomer or FAC isomer. Okay. Another case, see I am showing here clearly, it is first, it is second arrangement. Here you observe it. So in this structure, all 3 in same plane. How you are getting? See here, all 3 in same plane. 1, 2, 3. With respect to A you think, or with respect to B also you can think in both the cases. All 3 in same plane. If all 3 identical ligands in same plane, then we use meridional or mer isomer. Meridional or mer isomer. When? If all 3 ligands are of same type in same plane. Out of 3, if 2 in same plane, one is perpendicular to it, then we consider it as facial isomer or FAC isomer, meridional or mer. Very important JEE main question, repeated number of times. Okay. Next, other combinations I wrote here. Ma3B2C, how many geometrical isomers, different combinations I wrote here. So here you focus on this particular one, 15 geometrical isomers for MABCDEF, and different combinations I wrote. You pause the video, write in your notes all these examples whatever I gave. Database, because in exam every time, for example, if they give this one, if they provide this one, it's not possible to try every time 15 arrangements. It will take more time, making combinations. Okay. Instead of doing that, some data points, if you remember, it will save a lot of time. Okay, first you copy everyone till here. Okay, next moving to optical isomerism. Optical isomerism, first of all, non-superimposable mirror images are referred as enantiomers. Non-superimposable mirror images are referred as enantiomers. You can say optically active. Non-superimposable mirror images are referred as enantiomers or optically active. Okay, here enantiomers are optically active. For example, see here, if I take letter P, its mirror images is here, you will get like this mirror image. Exactly lift it up and place on this. It's not like turning, it's not like tilting. Lift it up and place on this. It is non-superimposable, meaning it will not fit on P. Okay, so these are not enantiomers. Sorry, here non-superimposable I wrote, these are enantiomers. These are enantiomers. But here you see superimposable mirror images. Here see letter A mirror image same exactly like it. If you lift it and place on this, you will get same. It is superimposable. So these are not enantiomers. These are not enantiomers. Okay. Substances which can rotate PPL are referred as optically active substances. PPL is plane polarized light. PPL is plane polarized light. Plane polarized light having vibrations only in particular direction. It's not like random. Plane polarized light is obtained when ordinary light passes through Nicol prism, so that ordinary light having irregular vibrations. But whenever it is passed through Nicol prism, it becomes plane polarized light where vibrations observed only in particular direction. So which can rotate PPL are referred as optically active substances. Such isomers are two types, dextroform as well as levoform. Dextroform we represent like D are positive, levoform L are negative. L are negative. See, dextroform rotate PPL. It rotates PPL plane polarized light towards right or clockwise. Levoform rotate PPL towards left. Rotate plane polarized light towards left. Okay, C ones towards left. Now see case 1 for tetrahedral complex coordination number we know it is 4. Optically active, these complexes are optically active if all 4 ligands are different. If focus on this, here 4 ligands are different. Only in one case tetrahedral complex shows optical isomerism, that is if all 4 ligands are of different type, then it shows optical isomerism. Otherwise it is not optically active. Next type, coordination number 4. Coordination number 4, that is we know DSP2 hybridization. Optical inactivities, square planar complexes are optically inactive due to optically inactive, you write clearly, reason also we mentioned here, due to plane of symmetry. Due to plane of symmetry, because we can cut square planar complex along the plane. Whatever different type of ligands you place, along the plane we can cut. That's why plane of symmetry makes it optically inactive. For octahedral complex, coordination number is 6. Like different examples, first Ma6 given, it is optically inactive due to plane of symmetry. Optically inactive due to plane of, because all are same type, right? You can, what is plane of symmetry? Plane of symmetry is imaginary plane which can cut molecule into 2 equal halves. Ma6. Okay. So for identification of optical isomerism, 2 important rules. Rule number 1. If any pair has same ligands, then it is optically inactive. What are these rules? We'll see now. If any pair has same ligands, then it is optically inactive. Rule number 2, if any two pairs are same, then it is optically inactive. If any two pairs are same, then it is optically inactive. Keep in mind these two rules you need to see. Any one rule is satisfied, then the structure is optically inactive. If any one rule is satisfied, structure is optically inactive. See now, Ma5B, here only one arrangement possible. Right? Here it is. So you see now, I wrote AA, AB, 3 pairs I mentioned. Rule 1, if any compound having same, if any pair has same ligands, it is optically inactive. Rule 2 also satisfied, 2 pairs are same. One rule enough to make it optically inactive. But we are searching for rules. Rule 1 satisfied, rule 2 also satisfied. Hence it is optically inactive. Next, Ma4B2. Ma4B2, AA, AB, AB. So different combinations I showed here. Observe it. Different combinations. Rule 1, rule 2, see here now. Here 2 pairs are same. Rule 2, rule 1, again rule 2. See, in each structure, you search for rule 1 or rule 2. If both are available, so no problem. At least one rule, if it is satisfying, you can directly write optical inactive. Structure 1, structure 2. Both are having either rule 1 or rule 2 or both are present. Both the rules are satisfied. At least one rule, if it is satisfied, you can consider structure as optical inactive. So no optical isomerism. Ma3B3, you see, pair having same ligands. Here 2 pairs are same, so optically inactive. Ma3B2C, just we made into different pairs, like how we made random pairs. You take these ligands and make into 3 pairs, which should not repeat. Rule 1 satisfied, here also rule 1 satisfied, rule 2 also satisfied. What is rule 2? If 2 pairs are same, optically inactive, no optical isomerism. Ma2B2C2, 5 possible arrangements I showed here. Total how many? 5 possible arrangements. How I made? Different combinations I showed. Like 3 pairs. Here if I see, for example, observe it. So here overall 5 arrangements we are getting. Out of 5 arrangements, see first one you see AA, CC, BB, AA. So here first rule 1, rule 1, rule 1, rule 1. For fifth compound, no rule 1, no rule 2. Hence, fifth compound is optically active compound. So remember, optically active compound is 1 here. Out of 5 structures, only 1 structure is optically active. But if they ask about optically active isomers, we consider it as 2. Why? Each optically active compound having 2 isomers. One is D isomer, one is L isomer. So optical active compounds, if they ask, answer is 1. Optical active isomers, if they ask, answer is 2. Okay. Ma2B2CD, here it is optically active. Why? If you arrange Ma2B2CDC, here if it is showing optical activity, still further different ligands we are using, it is optically active. Number of optical active compounds, here 2 you will get. MABCDEF GI, geometrical isomers 15 we studied. Optical active isomers 30. How? Here you can see optical active compounds first. Optically active compounds. Optical active compounds is equal to 15 here. But optical active isomers 30, because each compound having 1 D, 1 L. So into 2 if you do 30 you will get. Then MAA twice B2. What is the meaning of AA twice? Bidentate symmetrical ligand. It is also optically inactive. Which one optically inactive? Here 2 forms available. I will discuss about 9th one below here. I wrote under note. 9th one will see below. This one you see 10th one. Symmetrical, bidentate and BC. So here first structure arranged like this. Here second structure. Here you can see there is POS, plane of symmetry. So POS present, optically inactive. But here no POS, so optically active. Optical active compound means again D and L, 2 optical active isomers. Overall it is optically active, this one. Optically active, which one? Only one structure. One structure is optically active. But one structure is optically active, we can consider it as optically, one of the structures is optically active. Here in this structure, ninth one you see, ninth one I showed MA twice B2, separately I showed. Trans and cis form. So here B opposite trans. POS present, how we can cut like this. But here no POS. So it is optically active, optically inactive. It is cis form, it is trans form. So for given compound, optically active, inactive is trans, active is cis. You mark it as important question. Important question, MA twice B2. Out of 2, cis is optically active, trans is optically inactive. Okay. Next, a few more examples I wrote. This data you need to remember, every time difficult to frame combination. MAB3 type is optically active, MAB2 AB twice, C2 optically active. If they ask any question number of stereoisomers, then we use number of geometrical isomers plus number of optical isomers. Optical isomers, okay. That's all about isomerism part. Next, moving to metal carbonyls. Metal carbonyls are the compounds where metal combined with carbonyl group, that is carbon monoxide ligand. Homoleptic metal carbonyl, homoleptic metal carbonyl, heteroleptic metal carbonyl. Homoleptic metal carbonyl, all ligands are of same type. All ligands are of same type, CO. Here all ligands are not CO. Other ligands are available. See, like this one, homoleptic. Here it is heteroleptic ligand. Homoleptic, heteroleptic ligand. Okay. If all ligands are of CO type, homoleptic metal carbonyl. Heteroleptic, not all are CO. Other ligands also present like this. Most of the metal carbonyls follows EAN rule. And CO is strong ligand because it is strong due to back bonding or synergic bonding. You know back bonding or synergic bonding. What is back bonding? Here carbon monoxide form one bond with metal, which is sigma bond. In turn, after accepting electrons, metal also gives back electrons too, because as it is accepting electrons here, metal gets more electron density. More electron density is highly unstable, but due to which again instability increases. So in turn, to reduce electron density, it is giving back electrons to CO in the form of second bond, pi bond. You may get doubt, as it is getting instability, why it is accepting electrons? See, first for temporary it is getting instability, finally it is giving back electrons in the form of pi bond, so which results in two bonds. Whatever back bond here from metal to ligand is, we call it as back bonding or synergic bonding. So because of double bond, bond strength increases. In turn, overall result you have to see. Due to back bonding, double bond is formed, metal carbon strength increases. This carbon strength increases because double bond is stronger than single bond. Bond strength inversely proportional to bond length, so metal carbon length decreases. According to MOT, vacant orbitals of CO, according to molecular orbital theory of chemical bonding, vacant orbitals of CO are anti-bonding pi star orbital. Vacant orbitals, which are empty orbitals of CO, are anti-bonding pi star orbital. So here metal is giving back electrons to CO, right? Metal is giving back electrons to CO, but here empty orbitals of CO are anti-bonding. Whatever electrons given by metal, these electrons occupy anti-bonding pi star orbital of carbon monoxide. But here remember, if number of electrons in anti-bonding molecular orbital increases, stability decreases. Stability decreases. Before going further, bond order formula once you recollect from chemical bonding of 11, half into Nb minus Na. Half into Nb minus Na. Bonding molecular orbital, anti-bonding molecular orbital, electrons. Electrons in BMO, electrons in ABMO. If number of electrons in ABMO increases, bond order decreases. See, if this value increases, bond order decreases. Bond order directly proportional to bond strength. Bond strength inversely proportional to bond length. Finally, bond length increases. Okay. Very important note. Here there is metal carbon bond and then carbon monoxide. Between carbon oxygen there is another bond, CO bond. So if we carefully observe it, metal carbon bond strength increasing. Why? Double bond created because of back bond. Bond length increases because inversely proportional. The double bond is shorter than single bond. CO bond you see now. Bond strength decreasing for CO bond because electrons given by metal occupy antibonding molecular orbital. If Na electrons increases, bond order decreases, bond strength decreases. Same I wrote, bond strength decreases, bond length increases. One more important point, if negative charge on metal increases, back bonding increases. Why? If metal is having negative charge, immediately it forms back bonding to reduce electron density. Back bonding increases. Right? Next, back bonding increases, metal carbon length increases, metal carbon, what we mentioned here, see, back bonding increases, metal carbon strength increases. You write here, metal carbon strength increases, metal carbon length decreases, CO strength decreases, CO length increases. Okay, SEC, negative charge on metal, because it becomes more electron density condition, so that instability increases. So to reduce instability, metal give away electrons in the form of back bond. One example, see, JEE question. VCO6 minus, CrCO6, MnCO6 plus. Everywhere carbonyl ligand. Here charge of metal is -1, 0, +1. As we know, extent of back bonding directly proportional to negative charge on metal. A having negative charge minus, B having 0 charge, C having plus. So more negative charge, more back bonding. Hence back bonding, that is A greater than, B greater than C. Extent of back bonding. Okay. Next, types of metal carbonyls. Types of metal carbonyls, 3 types: monomeric, bridged or binuclear, polynuclear compounds. Monomeric meaning metal atom is 1, binuclear metal atoms 2, polynuclear metal atoms greater than 2. See here, metal atom 1, metal atoms 2, cobalt, manganese, metal atoms more than 2. So here metal-metal bond is referred as sigma bond. Wherever there is metal-metal bond, that is referred as sigma bond. Sigma bond meaning here, we know bond means 2 electrons, so 2 electrons we consider sigma bond. So delta bond. Sorry, metal-metal bond is delta bond, not sigma bond. See these structures you have to remember: CO2, CO8 structure. Here CO is cobalt and then respective carbon monoxide groups. Here in between there is delta bond. Structures you have to practice because structure based questions asked. Follow CAN. For example, you see question here, CO2 COX given. We know it is 8. We know it is 8, but how to find, if it is unknown to us, how to find X value? CO2 COX, find X, assume that it will follow EAN rule. Cobalt, next noble gas number is 36. After cobalt, 36. How many cobalt atoms? 2. So 2 into 36 I wrote. Plus atomic number of cobalt is 27, such 2 atoms available. Plus cobalt is monodentate, it can form one bond, meaning 2 electrons. Monodentate ligand, it can form one bond. How many such atoms? How many such groups? X. So 2x. Why we are writing 2? Because it can donate 2 electrons. Plus a delta bond also available here. Delta bond meaning 2 electrons contribution. After calculation, you will get X is equal to 8, which is CO2, CO8. One similar question. Once if you know CO8, COX question based formats given, so remember. Next, Mn2CO10. Mn2CO10 structure you remember. CO4CO12 structure, Fe3CO12 structures properly monitor. Mn2CO10, CO4CO12. How I show structures? You see, middle black color whatever I showed here, cobalt, surrounding carbon monoxide. Here all are carbon monoxide. Fe3CO12, all these are carbon monoxide. Structures we practice. Extent of back bonding directly proportional to negative charge on metal, inversely proportional to negative charge on ligand. For example, back bonding, here neutral ligand, negative charge ligand. The one with neutral charge shows more back bonding. Okay. So that is about total 3 parts of coordination compounds, part 1, part 2, part 3. So we covered theory part of coordination compounds in 3 parts. I hope all the concepts clear to each and every one. If not watched part 1, part 2, part 3, once again you go through these 3 videos and wait for the 4th video where we are going to cover JEE Mains previous year questions, JEE Advanced previous year questions plus some practice questions. So in upcoming video, we are going to discuss and solve few tricks, shortcuts to solve questions based on coordination compounds. Okay. Thank you. Thank you very much.